Welcome to the Todd and Noah Show, taking the mystery out of electric motors. Sounds ominous, Noah.
I'm thinking I'm going to hear Halloween music here.
Well, we just listened to Lights Out on the way down here.
We did classic radio.
Later than you think.
Yes.
Classic radio. We talked about zombies.
It was
They
scary.
talked about zombies in the 50s.
Good thing we had a fast car to run away from them.
Yes, it's always good to have a car that's adequate enough to run from danger.
Yes.
If necessary. Well, I have Noah Bethel, the Vice President of Product Development with us, and I'm Todd Gunnarsson, the Vice President of Sales and Marketing, and I know I cut Noah off. You wanted to say hello.
Normally I would say hello from sunny Tampa, Florida, broadcast from sunny Fort Myers.
Sunny Fort Myers. We're down here to check out some of the damage from Hurricane Ian, and I've seen trees.
Yeah, no, it's definitely a few snaps here or there. I think the further away you get from the beach, they've recovered quick.
Yeah.
Hats off to the recovery effort. That's a lot of hard work, I'm sure.
For sure. Well, Noah, this is part two of specialty motors, and we talked about induction and wound rotor motor in our first podcast. Now, this is our second podcast, and we're going to talk about the others, so to speak. Induction is 90%, wound rotor motors are maybe 5 to 10%. So there's another fraction, and this might be synchronous motors.
Synchronous motors, some people like to say.
Synchronous.
Synchronous, which just a spin on it, but it's definitely synchronous, I think.
Synchronous. Well, they must be.
It's like Target.
They must be from Carrier World.
That's probably the surface guys.
That's right. They only eat filet, and they only have the finest heavy cream in their coffee.
Never experienced that.
Right. So tell me about synchronous motors. What are they?
So
how do they operate?
Synchronous motors are quite fantastic in that, in the previous conversation where we discussed a slip, right, where the rotor has to be going slower than the stator, not the case with synchronous motors. And much like the name says, the stator magnetic field rotating roundy, and the rotor going roundy are going at the exact same speed, right? Now, in synchronicity, right? Like the orbital, satellites and geosynchronous orbit. It's a very good example. So I will say this. They're not perfectly synchronous all the time, and what I mean by that is there's always a little bit of dampening. Anything time you have a load change, you're going to have a slight slip. Well, it recovers nicely. There's a lot of torque to keep those two in line, and because they're all dampening windings, we'll talk about the motor shurs and stuff like that. But for the most part, if it's an 1800 horsepower stator winding design, the rotor turns at 1800, and that's what the synchronous is designed for. It makes sense if you need a constant speed, and I'm talking about a real constant speed. This is your motor, but there's a lot of other things that people use them for. We'll talk about as we move forward.
So talk a little bit about the construction of a synchronous motor then.
Right. We talked about induction squirrel cage and induction wound rotor motors. The stators were the same, and there's no difference with the synchronous either. The stator is still going to be a three-phase wound. It could be lap. I'll tell you this: most of the synchronous motors are not in the low voltage range. Right. They're almost all in the medium to high voltage, and they're used for we're talking thousands to many thousands, tens of thousands of horsepower. So they're
lower speed.
They often are. Yeah. Now and that kind of goes into some of the design criteria. But from the stator perspective, three phases of windings, not so different than any other AC induction motor. When it comes to the rotor, though, now we're talking very different, right? Remember we talked about the wound rotor had windings on the rotor, but it was wound in a wire delta configuration. Well, there's windings on a synchronous rotor as well. And let's start with like a salient pole. A salient pole design rotor has big coils wound around a core, and they're basically connected to the rotor, okay? And they're connected to each other in like a series winding. So very often we'll see 18, 24, 28 pole synchronous motors, and so you might have 28 individual field coils wound on this rotor, right? It's pretty intense. Now what they do is they wrap those salient poles with a mortise windings, which remember we talked about the squirrel cage?
Yeah.
Well, take a little squirrel cage and wrap it around those DC, and by the way, those are DC field poles, right? So as we move forward, we're going to talk about applying a DC power to those field windings. But the squirrel cage that they place over top of this thing on the rotor itself is designed to help it get started. We'll talk about that. But those are called amortisseur windings. It's hard to say and even harder to spell. So plan on, if you're going to write an article about amortisseur windings, look it up first. Otherwise, your technical editor will...
I never find myself in a situation where I have to spell amortisseur for something big.
Well, don't worry. We've got a good technical editor, and she will catch you every time.
So true.
It is. She will be on you in a heartbeat. So that's the rotor design. Quite complex. Now, similar to a wound rotor, you go to the end of that rotor shaft, and you've got to get that DC on those windings somehow, right? So it could be a set of slip rings. So we're applying DC through brushes, again, my favorite thing. Or it could be a self-excited, where there's actually a generator that sets out at the end of that rotor and it uses a generator to apply DC to the windings. We'll get into some of that detail. Now that's the salient pole. Just make sure that when you get higher than like 6 pole, when I say higher, I mean faster. Like if you go into the 4 pole synchronous motor, a lot of times those are going to be wound in like a turbo rotor design, or I think there's another a cylindrical rotor. Right.
So talked about startup of a larger synchronous. So how does it start?
So let's just walk through a startup in any given day. So somebody pushes the start button, rotating magnetic field is formed in the stator windings.
New guy pushes the start button.
Always a new guy. Unless it's already been proven, then you want to take the credit. So you get it started, the rotating magnetic field's going roundy. Now remember, there's no power applied to the DC field coil yet, but you do have those amortisseur windings, right? Or that squirrel cage. So just like an induction motor.
It's like an induction motor.
It absolutely does.
To try and latch onto that field.
Induces power onto these amortisseur windings. They create current and a magnetic field. It starts to turn. And at a certain point, usually it's a centrifugally switch driven, right? So it gets up to a certain percentage of the speed, 80, 90%, whatever the set point is, and then that the breaker or the contactor will close, DC power will be fed into those synchronous fields, and it will be a very strong energized magnetic field, which will latch onto the rotating magnetic field, and almost instantly you're turning 1800 RPM on a 4-pole motor, whatever it is. So that is pretty much the standard process. Now, once it's up to speed, the amortisseur windings are done, right? They're cooling off.
Not required anymore.
Right. Now, some of the designers, they'll tell us that, the amortisseur windings will dampen a heavy load change. We have encountered.
So you do slam load onto the synchronous motor, because the key is to keep speed consistent.
As consistent as possible, yes.
So to make sure that you don't drop a pole because of too much load, you want that amortisseur.
Now, if you start talking about, a pole slippage, it's a good point. It's a good.
You can talk about that afterwards, but I'm just talking about
that's like a catastrophe when you start slipping poles. That's such a current. So once it's, there's a little bit of dampening that they'll be involved in, but for the most part, they're cooling off and healing if there's any expansion that occurred during the startup, which is common. So once it's up and running, that's it. It's clear and running after that.
Okay, so we're fully operational then. We're running at the speed that it's the nameplate speed, synchronous. So talk to me about if you don't have, what are they used for? What are the uses in?
Right. A lot of the uses when it comes to...
we talked about speed. You want an application that has a constant speed. But there's other avenues that you can use synchronous motors, correct? Like power. I've heard for power factor.
I would tell you that often there's a dual purpose. Yeah. So even though we've seen them a lot on compressors, we've seen them occasionally in pumps, but compressors are a real popular use for them. But there's always a side interest, right? So with synchronous motors, one of the things that's interesting is when you have control of the field that you're applying onto the rotor, you can adjust that, right? And by adjusting the field, you adjust the power factor, right? So a lot of people will look at, hey, do we have an application that needs a steady speed that would be like a compressor, and at the same time, we can offset some of our power factor issues, right? So keep in mind when a utility sells power into a plant, they're requiring you to operate at a certain power factor. And the more inductive loading, inductance motors, different things, the more you add to the plant distribution system, the lower you tend to make that power factor, and you have to compensate for that somehow. And it's a serious issue to the tunes of millions of dollars for plants that have a lot of industrial applications. So let's say if they say, hey, if you go under 0.85 power factor, we're going to penalize you, right? So as an example, that's just a number I'm throwing out there. But if you start a motor up and it causes the power factor to drop down below a certain amount, and they monitor that, they're going to assume you do that for the whole year most of the time. So you're going to be penalized, even though maybe they caught you one time, you're going to be penalized the whole year for that. Not to give too much detail, but there's a lot of money involved, right? So what you can do is go ahead and buy a synchronous motor, apply, use it to work the application you want, but then turn around and overexcite the field just enough what it does is it creates it increases your power factor closer to unity. In fact, a lot of the synchronous motors are running in a leading power factor, right? So current is actually leading voltage for the exact purpose of modifying the power factor to prevent themselves from getting too low and potentially be in trouble with the utility plant.
Yeah. You don't want to be in jeopardy with that. So those are the uses for them. Now, let's talk about, you talked about construction and how they come up to speed. What types of data can be collected on synchronous motors, or what should you be collecting?
Good question. Have you ever heard me talk about my favorite test?
I know you have a lot of them.
Yeah.
Now, after hearing you on Wound Rotor, I thought that was your favorite motor. But I think inrush is one of your most favorite tests.
Absolutely, and I can't say enough about the use of inrush as it applies to a synchronous motor. Why? Just because of the operations that you and I just went through. That's a lot of complex stuff going on. You're starting it as an induction motor. You're getting up to speed. Are you getting up to speed? Is the centrifugal switch working like it's supposed to be? Is there a field pole that's causing problems? There's all kinds of things that can go wrong. So out of the chute, if you don't have a baseline inrush startup test, and by inrush I'm talking 3 phases of voltage, 3 phases of current, make sure in case there's a new listener, 3 phases of voltage and current, 6 channels through the entire startup process. We want to see when you push the button, how that reacts to each other phase to phase.
And you can actually see windings drop out, and can you see it go into synchronous?
Oh, absolutely. Yeah. It is so easy. And in fact, here's an important role in that. When you hit the start button, with the same load that it always starts with, and keep in mind, we're not talking about a high torque startup on synchronous motors. They don't have it, right? So you're not going to start these at a full load. There's going to be repetitive starts for it. So when you start that motor and you get through the inrush and the amortisseur windings are getting the motor up to speed, it should be a consistent time to synchronization, plus or minus a little bit.
Yeah.
But if it takes 3.5 seconds, for this motor to get started, or 3.5 longer, you've got a problem. Now the question is, what would be the problem? And there's nothing more evident than when you say, hey, it's taken 7 seconds to get this thing into synchronization. What has changed? Well, we heard a report once from a paper industry. Paper industry has a lot of chemicals that treat the paper product and that kind of stuff.
Right.
Guess what used to attack the solder joints at the end of the amortisseur windings or the squirrel cage? Whatever chemical they were making or using. And so one of the technicians noticed that
high resistance connections,
or no connections at all. It literally was eating the solder joint completely off. Absolutely. And so the technician was finding pieces of the amortisseur winding outside the motor. Now, no big deal. It was an open frame synchronous motor. Sometimes you can actually walk up to a large synchronous motor, 28 pole, and you can literally see into it, right? It's an open frame, a little bit older maybe. But what was neat about that was he saw that visibly. They should have been catching that on the startup test, right? They would have if they were taking it.
If they were doing it.
And good luck starting it up again, right? If you're seeing pieces of the amortisseur winding laying outside of the motor, it'll continue to run synchronous because the amortisseur windings aren't being utilized that much, but good luck starting it up again.
If you lose just one amortisseur winding, will it start, or what?
It will, just like a broken bar.
Like a rotor bar.
But guess what'll happen? It'll take longer, just like we were saying. So if you have less torque being created by the cage, as long as it's not flying apart and shorting things out, it will start up, but it may take twice as long or 3 times as long. And so until that centrifugal switch. Now, another situation is, what if it's not on a centrifugal switch? What if it's based on a timing situation and you're not up to speed and you try to slam in that DC field and now you're going into that pole slipping because it's not holding on, right? It's not in a good spot.
Of a gap between them.
Right, and it can create a lot of current and melt a lot of things, so you want to stay away from that. So inrush startup, my favorite, love it as a synchronous motor.
Absolutely, always do an inrush.
Always. After that, you're going to apply the same power, the same fault zone analysis, through the stator, looking at the impedance and inductance and resistance and all that.
So voltage should be balanced. Current should be balanced.
Absolutely. You want to verify the power factor.
Should be low. Power factor.
Absolutely.
Should be where it's supposed to be. harmonics should be low, all of that.
Yeah, one of the things to be aware of is there oftentimes is in these large compressor factories, like if you got, in the petrochem industry, there's a lot of times you'll have 3, 4, 5, 6 big synchronous motors compressing, liquid and stuff. So when that happens, keep in mind, although we talked about the different designs, right? You have self-excited, which means that DC power is coming from somewhere, right? I'm sorry, not self-excited, externally excited. My apologies. So that's coming through slip rings. Well, where's that power coming from? Well, they don't have big batteries sitting outside the plant there supplying power. So they have a DC, basically inverter, right? You're having a field regulator. So they're applying power to the rotor, to the DC fields, from basically a drive, right? It's more often called, a field regulator, or a field inverter. So basically, that's a nonlinear power supply, right? So you got a lot of harmonic content, a lot of energy. Well, guess what shows up on the stator windings as a result of this thing running? Even though it's running synchronous, right? There shouldn't be any induction. When you have harmonics in and out, you're going to induce those harmonics across the air gap into the stator windings. It can be pretty extreme. I know we were helping a company try to track down a harmonic source, that was throughout the entire company. Ended up being the compressor building when 4 of these big synchronous motors were running, and it was literally pushing it through the whole plant. What can they do about that? Usually a power quality engineer comes in and sees what they can do to filter it, reactor it, do something to try to clean that out.
So what about current signature analysis? You talked about inrush startup as being able to determine rotor, but do we see pole pass sidebands?
Not long enough. Not long enough to be effective. Now, there are some people who say, well, I'll just turn the synchronizing off and let it run as an induction motor for a while. I don't advise that because the squirrel cage or the amortisseur windings, as they're called, they're designed to help it get up and running, right? They're not designed to run a long time. And I would say you're risking the life expectancy of your amortisseur windings, which are critical, as you can say, based on our operational discussion. So, pole pass sidebands is kind of out of the picture, okay? But again, that's where the inrush startup takes over.
So we don't focus on pole pass?
We do not, no.
Okay. And then offline. Is there anything offline we can do?
Offline's almost never limited because you've removed power. It's just what can you get access to. And similar to the wound rotor motor, a synchronous motor offers a lot of things. So, you can apply offline tests to the stator windings looking for balanced and inductance and resistance. All that should be fine. Look at the standards that are built into your software and alarming you on insulation, contamination levels, all that. Rotor in the field, right, now it's a DC field, but we still want to do polarization index testing. We want to do, inductance measurements. Now again, it's a DC coil, so if you have like an 18-pole DC motor, they're all connected in series. And so when you measure that inductance, that is such a powerful tool. And we've got such great case studies coming out of, I believe it's the paper industry, where one of the common tools that are applied in the field for synchronous motors is a drop test, right? An AC drop test. Field engineer will come in from the motor shop or whatever local repair facility or service industry.
Complicated test, right?
It is, right? They basically
intrusive test.
It's very intrusive. It's a good test.
It's a great test.
It's a great test.
It's very intrusive.
It is. You're usually digging in, right, to the positive and negative or the input and output of each coil. Yeah. You're running 120 volts or whatever and looking at what kind of voltages, what kind of voltages drop per coil, right?
So wouldn't it be nice when they come in to say, hey, I have a change in inductance?
It is like night and day simplicity.
Because now there's a reason to come in.
And it changes a lot. Now, if you got to make math easy for me, if you've got a 10-pole synchronous motor, and when you measure the inductance, it is, let's say, 100, that's not even smart, let's say 500 millihenries as an example, right? So when you measure that, and that's your baseline, well, guess what has happened if it goes from 500 to 250? You've lost half of it. You've lost, 5 turns basically, right? And I'm not saying it's a 1-for-1, but the example's still good, right? And so when you see that, now keep in mind, you can lose multiple coils in a synchronous motor and still operate in synchronous speed, but it does get weakened. A lot of times if they see a bad field pole, the shop will just cut it out, cut the opposite pole out, and instead of a 26, you're now a 24 pole, right? It still operates at the synchronous speed. It's just you've lost a little bit of the capability. But being able to track back that inductance over time is so easy. And what ends up happening usually is like, hey, I've lost 30% of my inductance. I've obviously lost a couple coils. Then you bring the shop in and say, hey, what do we have? And if they do the drop test, put, like I said, 120 over the entire coil set, measure the voltage drop on each one. It's easy to find the one that's bad, right? And once you've assessed how bad it is, then they can give you advice. Do you want to try to cut some coils out in the field and keep operating, or do we need to
schedule a repair?
And sometimes those are intense. I remember.
Cheap.
No, we saw a 20,000 horsepower synchronous motor that had to be sent across the city of Houston, and it required a permit and a special truck, and it was a big deal.
That is a big deal. So I think you've covered just about everything on synchronous.
I didn't focus much on the excitation of a self-excited, and just to make sure, because I would argue that today I believe there's more self-excited synchronous motors that we run into. Now what we're talking about is a generator, an exciter that it runs, and it basically creates power and sends it through a rotating diode assembly, effectively. So it starts as an AC signal, goes through a rotating diode assembly, and provides the DC power to the field. Now what can we do with that? Well, nothing while it's rotating, right? We're not going to be able to test something while it's rotating because we're just not fast enough, right? We can't go roundy with it. But you can test the stator portion, the stationary portion of the generator, and that's critical, right? So we can look at that and make sure that the generator itself is balanced, and so that's what we generally do when it comes to a self-excited. The other thing is, if it's offline and you are going to test that field, we want to know what the inductance measurements, like we said. The inductance is such a good trend tool on that. You need to disconnect the rotating diode assembly. Find the bolts, disconnect it. Well, right. No reason to apply high voltage. The manufacturer of the diode assembly is never going to approve you to put high voltage across the diode assembly.
So that kind of puts a nice bow on the synchronous types of motors. Not that frequent out there, but they are out there.
And they're critical. Always a critical application.
Always critical application. And so that brings us to another, not as many anymore, but they're still out there, DC motors.
DC is, it's interesting because, again, I like DC because you got access to the armature, access to the series winding.
Direct current motors.
Direct current, that's right. And so they are workhorses. I mean, these things they appear a lot in steel industry. If you're trying, and man, they're so strong, but they're a maintenance hog. Right? In the submarine, we had them. It's the commutator, handbook can't say enough about it. It's there's a lot of things that can go wrong with that type of environment. And you have to be on top of it. It's got to be irregular. You can't just rely on technology.
That's where your commutator slip ring handbook comes in.
It is a big help, even for the visual aids that it gives. And when I say visual, as good as our technology is, and we use it all the time on DC motors, you still need to walk down and check out that DC motor with your eyes. You need to get down there and be close to it. So that's part of the DC. Again, one thing that we highly recommend that's grown in popularity is get a good baseline with the series, the interpoles.
Well, before we jump into that, what the construction of a DC motor?
Okay.
Like what is the makeup of a DC motor?
Right. So in general, you'll always hear reference to the armature winding and the series windings, right? So the armature in general is kind of always deemed as the working element of a rotating piece of equipment, whether it's a generator or a motor, actually. So the armature,
the rotating aspect
in a DC motor, it's the rotating armature. So you've got basically, and quite honestly, it's when you look at the rotating element of a DC motor, it's wound a little bit like your normal induction stator, right? It's lap wound coils, that are around this rotor, and they're the armature, I'm going to call it, and it's connected to a commutator, right? So the commutator is a bunch of bars, effectively round around the commutator ring and connected to those individual windings. Now, a lot of times you'll hear words like progressive lap wound DC armature, right? That just means that they're progressing one bar at a time, and sometimes they have wave wound, which the commutator bar goes into the winding here, but the 10 commutators away is where it comes back. That's a wave wound, right? I think more often we see lap wound. Again, that really does affect the person testing if they're doing bar-to-bar testing. But as far as construction, they all look the same, right? So from the slip, or when you get out of the armature windings, again, wound like a 4160 volt, AC induction motor around the rotor, though. It goes to the commutator, brushes set on the commutator, and basically that's where the power comes in and out. Now, a lot of times you'll have, like you might have 4 brush boxes with brushes, and you can have a lot of brushes, right? And so the big concern with that is arcing and sparking, which we'll get to as we get through it. But on the stationary part of a DC motor, Remember those salient pole synchronous windings we were talking about? Well, they install those onto the stator of a DC motor, right? So you've got these big coils, and here's what's magic. Next time you get a chance to look into a DC motor, you'll notice wound around those big, we're called the series pole pieces. Wound around, you'll see two different sizes of wire, which is kind of interesting, right? You'll see a bigger grade of wire, as far as the circular mills, and then you'll see a really fine. That's the difference between the series and the field windings, right? So, with the big ones are the series windings, right? Higher current, a lot of stuff going through it, and that does a lot of the work, right? But then you got the field, which is really more the speed control side of DC motors, around the same coil, right? And so that's kind of neat. Now, it's not that you're going to always have separate access to those, but a lot of times you will. When you take off the connection box and you look, you have A1, A2, S1, S2, F1 for Frank, and F2, right? So when you see that, you've got a big advantage of isolating faults because you can actually check those separately. Keep in mind, a lot of times there's a jumper. You'll see a jumper between the series and armature windings. So when you apply DC into this stationary element, it goes through the series and the field poles, and then it goes through the brushes into the armature winding. So it's the same current flowing through it all, right? So they've been around forever. I mean, this is the whole, Tesla versus, the AC versus DC thing. DC
Been
was
around forever, but they are getting phased out now.
They are.
When we recommend testing DC motors, we always look for like DC motors to compare the data to, because you're not getting the imbalance because you're only doing A1, A2, like you said, F1, F2. So there is no third one there to kind of develop a imbalance.
Thank goodness, in almost every situation where we're involved in troubleshooting DC motors, there is one like it, right? And it is like a saving grace, because you hit it right on the nose. If you don't have other coils, like, three phases to compare to each other, what's good and what's normal? C-story, we were troubleshooting at a Corvette, plant. They basically beat the winding harnesses of your Corvette. Not your Corvette. Your Corvette's newer than this one, but
Who are you talking about? What?
Yeah. So I don't know what your harness looks like, but back in the day, we were doing some. So we were say, hey, the complaint was operations, and usually that's the first people who see a problem with DC motor is whoever's operating it. It's operating differently. It's acting funny. They don't know the details, so they just know it's wrong. And a lot of times, don't ignore that. That's usually their best indication that whoever's operating it is sensing something different. So we get called in and we test this DC motor, and we're like, okay, we have values. It's not grounded. We have series winding inductance. We have armature winding inductance. But without a comparison, we don't know, right? A lot of times the nameplate doesn't give you enough information to make a decision on that. Well, guess what? One just like it, other side of the plant, we measured it. The one that was out acting up had half the inductance. They had basically a turn short on the field coil. And so it was a big deal. So it means operations got sluggish. They couldn't control the speed as well.
I'll add to your case study, we've had one as well. It was at a tire manufacturing, and they had the same thing, but they didn't measure inductance, and they didn't measure resistance. But they did measure resistance to ground, and guess what? Resistance to ground was fine. There was no issues there.
Happens too often.
That's why it's so important, what you said, to have that change in inductance, to have that change in resistance and compare it to its like motor.
Absolutely.
It'll tell you unequivocally that there is an issue with that. And if it's running hot, that insulation will break down, and you will lose turns, and you will change your inductance, and you will change your resistance measurements.
Can I tell you that with inductance, I would have gotten more sleep on the submarine?
Oh.
We were asked to save the world with a multimeter and a megometer.
We got nothing but sleep. So many people on
it's
it.
just
We
not
were on
fair.
5 and 15. You had 15 hours that you had to figure out what to do.
We didn't.
What was your schedule?
We were working on a three shift.
Did you hot rack it with anything?
Thank goodness I didn't have to.
Never had to hot rack.
No, I think that was reserved for the really brand new guys. In the nuclear engineering side, we got lucky and we weren't required to do that. But yeah, no, sometimes you didn't have your own rack.
What was your shift?
We basically did 18-hour days, so it was 3 6s. So
we're 6 on.
6 on.
It's 12 off.
Right? Well, not really. Yeah, we had 6 on, 6 hours of maintenance with with carbon brushes and slip rings, and then we're supposed to get some sleep, right?
Yeah.
So in a given 24-hour period of time, we almost always have 18 hours of work, which is a long day.
Yeah.
Having to help you if you ended up doing drills, and then you'd end up, basically losing out your sleep, and so now you're going back to another 18 hours, 12 hours.
The beauty of being on a carrier, if there were flight ops, you didn't mess with the plan.
Ugh.
That was the beauty of having.
I think the only time we got real sleep was when we were close to an enemy submarine, and everybody had to be quiet.
You had to be quiet?
Yeah, get in the rack, don't say anything, don't do anything.
Yeah, the worst we would ever do is 5 and dimes. They call it 5 and dimes, 5 and 10, 5 on 10 off. But we were never that on our carrier. So, Noah, what are they? So you talked about DC motors, and it kind of leads us into our next. It's not really a motor, but it is an application that's kind of taking over for DC motors, which is variable frequency drive.
So popular. I can tell you, if you said in our...
Use DC motors used to be for speed control, right?
Speed control and heavy torque, heavy use, they're strong as an ox.
But we said they're being phased out.
They're inefficient, they're expensive, they're large, they're massive.
Not everybody knows about them anymore.
No.
So they're not hard, but if you're not familiar with it, it could be complicated to work with it. But variable frequency drives, talk to us about them.
So the magic of variable frequency drives is you can take an AC induction motor and control the speed like you could with a DC motor, and the better they get at handling high torque environments. Even in the steel industry, you're seeing these massive DC motors. Now, the largest I've ever seen was an 8,000 horsepower DC motor, and I can tell you it was 2 stories tall. It was if not more. It was huge, and they're able to take motors in AC types and connect it to a VFD with good speed and torque control, and literally reduce maintenance and costs and everything. Now, it's not like no work at all. Obviously, drives can fail as well, and we have to monitor that. If you sit in our tech support department, 25 years ago, the main conversation was, is it the motor or is it the pump, right? Well, today, very often, is it the motor or the drive?
Yeah. And
that's probably the majority of the conversation. And there's a lot of troubleshooting on what the motor's doing and what the power quality, power circuit, and all that. But those drives creep in every day, and they're not going away.
Well, the interesting thing about drives is when we test them online, which is the only way you can really test a variable frequency drive, they should have some similarities. It should be balanced voltage, balanced current. You can still see pole pass if it's in the...
Absolutely.
So there's a lot of similarities.
We call it balanced but ugly, right?
Right.
If you're used to the simple sine wave, it's a nice, smooth, clean sine wave. Well, that's not what happens in a variable frequency drive. We're using a DC bus, effectively, and turning that into, or synthesizing, an AC sine wave. Now, if it's a DC motor that we're applying drive to, it's different. It keeps it at the ripple DC. But most often, it's an AC motor, right? So you're basically converting AC to DC, and from that DC bus, you're firing voltage, whether positive or negative, in like a pulse width modulated format, and that is creating a synthesized AC signal. It's amazing, but
we can actually see that in our current signature analysis spectrum, saying what is the dominant, because if it's a 6 pulse,
right,
it's 6 times the fundamental frequency.
60 hertz is an example.
So the higher math puts you at 360 hertz, is where, when you look at the time domain,
it's one of the first things we like to look at. You get a basically a current spectrum view of the DC current going to the motor, and you're absolutely right. The 6 times 60, 360 hertz is the dominant frequency.
Should be the dominant frequency, because we have case studies that show when you're breaking down, and one of the SCRs or whatever is breaking down, and it's not passing the ripple.
Right.
It starts to pass an AC signal. Now the 60 hertz becomes dominant.
Right. A simple way to try to get it to express it visually is if you have 3 phases coming into a rectifier to go to a DC drive. What the DC drive basically does is take the negative part of that sine wave and flip it up. So now for any given phase under a cycle, you have 2 peaks, all in the north, right? Well, if you do that with 3 phases, you have 6 peaks, and 6 times 60 is 360. Well, if for some reason a rectifier section of a drive starts to fail and you lose 2 of those peaks, then you got a flat line and then 4 peaks, or 4 positive cycles and then flat line. It's not supposed to happen, right? And that 360 hertz changes. But man, to get a baseline spectrum on a DC drive, DC drive is so nice to see, and it's good to have.
And we can also look at IGBT type firing on variable frequency drives. We may not get that initial because of the speed of that fire.
You bring up a good point. One of the concerns with the newer technology and the IGBTs, as you mentioned, the insulated gate bipolar transistors. That's a big word. But that fancy technology.
It's big for us.
It's big for us, yeah. It's hard to say. I need more coffee.
It's actually more than one word. But
it is. It's four.
Hopefully they don't. Hopefully it's not just one word.
I tend to run. Our friends from the Carolinas always run those words together. It's not as hard to say. But anyway, when those transistors are firing, there's always going to be an inductive kick that occurs. For the most part, if you're involved in troubleshooting and you wanted to look at an individual transistor, usually it's not your motor technology that's going to be utilized for that. You're going to end up grabbing an oscilloscope, and taking a look at that, because we're talking 0.1 microseconds, 0.2 microseconds.
But when it's not operating correctly, we can surely see something.
If it fails, it shows up big time.
Firing in the wrong direction when it should be firing in the negative, and it fired in a positive.
And what a great case study on that. Yeah, that was, I think it was a vertical pump at a municipality, right?
Yeah, it was a municipality pump. Showed tremendously. It was shaking the floor.
It was shaking the floor. That's right.
That's and ended up. Noticed there was a problem.
We take one time domain capture at 53 hertz or whatever.
3 hertz, whatever that is at.
And we were getting negative cycling of power during a positive cycle. So it's almost like hitting an electric brake once every 60 cycle, or every cycle, 1/60th of a second. It was, and as a result, you can imagine the vibration. They were concerned about literally the mechanical structure after that type of use. But we were able to simply isolate it to a card, pull the card out, put a new one in. Day was done.
And initially it was look at the ground. Resistance ground.
Isn't it funny how they do that? Well, the manufacturers are smart, and I'm talking about drive manufacturers, right? And so if you guys are out there, you're owning drives, and you feel like you got a drive problem, and you call the manufacturer, and they're like, well, check the insulation on the motor. And you want to be like, what do you mean check the insulation on a motor? That doesn't make any sense. It makes a lot of sense, actually. Because what will end up happening is if you get a bad neutral reference, a lot of times drives decide, when they're going to advance and when to fire based on that, that ground reference. If that ground is in and out, all of a sudden you got a confusion point with the drive, regulation. That's what we were getting on that drive. It was firing negative at the wrong point in time, and as a result,
it could be a grounded motor is what you're talking about.
Yes, which is confusing, right?
It's confusing the drive.
And we've seen this, right? We had a case study where, there was water actually, up inside the conduit, the conductor itself, not the conduit, but the actual winding insulation. And it was creating a lot of confusion. They had replaced 3 drives, maybe 4.
$45,000 a piece.
It was huge.
You're talking $180,000 for 4.
And we hear this a lot that, well, do I replace the motor? Do I replace the drive? Or do I replace the cables, right? For the most part, surprising to me, guess which one the industry says is easiest to replace? The drive.
Probably.
Which is why they went through 3 drives, 4 drives, and it was over. And now I think the hardest of all might be the motor, but even the cables. Cables are hard to replace. So.
I always wonder who benefits the most from that decision, right?
That's a good point. Not the new guy, I can tell you that.
Not the new guy, that's for sure. Well, that brings us we might expand. There's other applications out there we could go on for hours on the different types of motors we've come across, but maybe not. These are the largest portion that we do. This probably represents 99%
for sure.
Of the motors that we would come across.
Robotics and servos are becoming a popular thing, and certainly...
But not as much as you would...
Very industry specific.
Very industry specific. So I think we're going to wrap up this part 2 of our, we talked about the synchronous motors, we talked about DC motors, we talked about variable frequency drives, and spent a good long time analyzing all of those and how to test them and what's the construction of them. So with that, as always, we hope that you were able to get a tidbit of information out of this, hopefully a lot more than that, and make probably a better tomorrow for you.
It's a good goal.
Simpler tomorrow. Easier tomorrow. More efficient tomorrow.
Amen.
A more efficient tomorrow is always good. We appreciate your time, and until the next time we talk to you, you guys have a great and safe day. Thank you.
Thank you for joining us for this episode of the Todd and Noah Show. We will be back for another episode very soon. In between, we hope to see you in the Mobius Connect online community where you can network, learn, and share with Todd and Noah and other industry professionals at mobiusconnect.com, and we will see you there soon.